Hello and welcome back to another video. In today's video we're going to be talking about defensive and offensive programming. Alright, there really is a lot to cover in this video, so we'll start out like this. We'll talk a little bit about normal programming, and the reason for that is because a lot of people say certain things are defensive programming, but they're not. They're things that you should be doing in all programming. So we're going to handle those misconceptions first. Then we'll talk a little bit about offensive programming, and then we'll finally finish off with offensive programming. All right, so let's go. A normal programming basically means to have all of the checks that are necessary in your code and to handle certain errors as well. Okay, and those things are not optional. You have to do this for all programs. And if you don't do them, your program is not going to be good, or it's going to be buggy. It's not going to work. So let's start with the checks, okay? So some examples of checks you might have in your programs are things like null checks, right? You need a lot of null checks in your code, a lot of conditionals, as we've seen in the null checks video, okay? And you might have so many that it might feel like you're being overly defensive with your code. That is not the case, because the fact is that if you miss one null check, you have a bug in your program. There is no question about that. You definitely have a bug. So this is something that you must do, whether or not you're doing defensive programming, right? It's not defensive programming for you to have these checks. And the same thing applies with handling certain errors, right? So for example, kinds of errors that are expected and outside of the program's control, your program should always handle them, okay? And for some examples of that are things like failing to send a network request because the client's connection dropped, okay? And the user providing invalid information in a form or something like that. So a few things with this, right? So first of all, if a program crashed on these errors, that would just be an awful user experience, right? First of all, they might have done it by accident, like they might have submitted some invalid information by accident. It's bad for the program to crash, right? It should instead just say, hey, you need to submit correct information. Here's what you did wrong. And also, it's very easy for all programs to handle these things, right? A lot of the time is just show a message to the user and ask them to try again. So defensive programming or not, these are things that every program should do. So these things are categorized under normal programming, not defensive or offensive programming. All right, finally, what to do if there are bugs in your program. So under normal programming, well, we've said a bit about what to do in the other video on how your program should respond to errors. But under normal programming, you don't generally tend to handle those. That is indeed where defensive programming comes in. All right, so enough of that. Let's move on to defensive programming now. So basically, in my interpretation, defensive programming is about fault tolerance, okay? It means to go above and beyond to really ensure that your program is going to continue running and it's going to be bug-free, okay? That's defensive programming. And it's used for certain types of programs where we need maximum availability, safety, and security, all right? So one example use case of where you would definitely want defensive programming is something like NASA space exploration missions, all right? So with this kind of thing, you have a little robot thing, right, that has some program, has some code to run it, and you send it off to space, okay? And if anything goes wrong with that code, that's billions of dollars worth of work lost and years worth of work lost, okay? So nothing can go wrong. Everything must work basically perfectly, or at least certain critical parts of the code, such as, for example, for restarting other parts of the robot or for communicating back and forth with Earth, right? Those critical parts must always work. The rest, maybe you can fix with a software update or a restart, right? But certain things must always work. They must never go wrong, okay? So that is where you do a lot more to ensure that compared to just normal programming. In comparison with most normal software, first of all, even if it's buggy, it might still be usable, okay? Secondly, even if, say, an order can't go through, no problem. The customer can call customer service. Like, it's not the end of the world, Or if your program has a problem, you can just crash it and then the user can restart it, or you can restart a particular server that has the error, or you can update the code, or you can even go to the physical server and restart that, right? If you're AWS or something. You don't need to have super safe code for the majority of programs, at least compared to the NASA example. Anyway, so having said all that, how do you do defensive programming? Three main things, in my opinion. The first one is to have extremely good software development practices. The second is that defensive programs tend to have a lot more checks to double check and even triple check that things in the program are still working as expected, that things are still correct. And thirdly, optionally, and this is a more extreme one, you might also have error recovery. So if you discover a bug in your program, you might actually do what you need to do to get the program back to being correct again. So normally for normal programs, you don't tend to do that. You just tend to crash the program or ignore the bug, okay? But with defensive programming, you might do that. All right, so let's go through them one by one. All right, starting with having very good development practices, okay? And the reason for that obviously is because you want the software to be as bug-free as possible. So what that means is you need extremely strict quality assurance, very thorough tests, very thorough runtime monitoring, very strict coding and development standards. And in fact, you may even not allow certain techniques and patterns, like for example, recursion. You also want good general software quality, source code that's easy to understand, and software that behaves in a predictable manner and things like that. So these points are obviously important for all software, but they're even more important for defensive programming, right? Because if you don't do this, then your code's going to have bugs. So what's the point of implementing additional measures on top of it with defensive programming, right? This is the first step. Anyway, so that brings us to the second step, which is having extra checks. So basically code with defensive programming tends to have a lot of extra checks in the code, okay? And those checks are there to try and catch bugs in the program. Like they're not checks that are necessary. Like if your code definitely didn't have bugs, you wouldn't need additional checks, okay? But these checks are there to catch those bugs. So they're defensive checks. They're not normal programming checks, right? What you do is essentially you have some condition in the code that checks whether something like some state or some value or something like that is valid in the program. And if it's not, then it shows that you have a bug. So if you have a bug, what do? Your two options are, if the program is in development, then you can crash the program and you can fix the bug right then and there, okay? And if your program is in production, then if you have implemented error recovery mechanisms, which is the next point, if you've done that, then you can start running your error recovery code to hopefully recover from the error, okay? Now, the common case is to crash the program and fix the bugs, okay? That's obviously best because, well, the idea is that if you've tested your program a lot and you've caught all the bugs you can with additional checks, then hopefully by the time it hits production, it's not going to have any bugs. So that's the ideal. And another benefit of these checks is that you catch the bugs earlier, right? Like if you check at different times that the state is fine here, it's fine here, and it's fine here, then you'll catch the bug right away. You're not going to catch it later on whenever the program happens to crash. And if you catch bugs early, again, you can debug them early, and the stack trace is going to be closer to the source of the error, so it's going to be easier to debug, and all of those good things. And finally, the sort of last point we mentioned here is that if you implement your error recovery, then the sooner you catch the bug, the sooner you can run your error recovery code, all right? Now, in terms of what checks to have, you can have as many checks or as few checks as you need, and you'll have to decide what checks to have based on risk analysis, right? So basically, what are important checks to have and what are less important checks to have and how much do you care and things like that. So for example, some things that might be important are checks involving important calculations and data that you obtain from places, right? So it's probably important for that code to work correctly, so you would check that. And arguably other smaller things are things like checking that functions have been called with the correct arguments and, constantly checking that state is in a correct state after simple operations and things like that. So here's an example on the screen where you're checking function arguments, right? So the function foo is called with two arguments, and you start out by checking, hey, are the arguments that this function has been called with, are they correct? Okay, so that's the if statement in there. And if they're not correct, you have a bug, so you can either crash the program, or you can handle the error here, or you can throw an exception to handle the error somewhere else, or you can do anything else that your error recovery mechanism has, right? Like I don't know, if it works through events or pub/subs or something, then maybe you have that in there, right? And then another example is taking results involving data. Now, I don't have a code example for this, but basically, normally you validate some data when you first receive it, right? Like when the user sends it to you or when you obtain it from somewhere, you validate it. And then you're going to have tests that the code you use to work with that data, right? You're going to have some code to transform or process that data in some way. You're going to have tests that that code is working. Now, if the initial data is correct and the code that processes it is working correctly, then the final result should be correct, right? You shouldn't need additional checks on the final result as well. But if you're doing defensive programming, you might have the additional checks anyway. You might want to double check that the data really is correct, right? So you might validate the final result as well. All right, and that's it about the checks. And the next point is trying to recover from unexpected errors. So the points mentioned so far, they try to eliminate bugs in your program. But having done all that, your program might still have bugs, unfortunately, right? So as an optional additional step, which tends to be more rare and it can be quite difficult, is to have error recovery from bugs in your program. So you're not recovering from like things outside of your control. You have encountered the bug and you're trying to recover from a bug, okay? Now, this can be quite difficult and it might require a lot of thinking on how to do. And it might even need to be part of your feature planning, okay? So for example, it might be the case that while your program is recovering, it needs to respond to a user. Now, this user-facing behavior is probably going to need a product manager as well when deciding how it should be, right? Like programmers don't tend to decide on their own what the user-facing behavior should be. Product managers tend to have a big say in that. So it might need to be part of your feature planning, how to recover from these things, right? And another thing is that error recovery might be a large part of the code. So as a made-up example, right, we're just making this up here, but consider that you have a backend and it accepts network requests to process orders or whatever. And while processing one of those orders, a server might error. Okay, it might crash or something might go wrong, whatever it is. So there are a few things that are possible for you to do in this situation. Some of them might be some things like this. You could have an initial server record the order information right ahead of time so that it's not lost if the erroring server can't do it, right? And then you might have some recovery mechanism for the faulty server itself. So for example, some other process may restart it, or maybe the server may try to fix itself, like fix its own state internally and things like that. And then finally, the order can be given to a different server, or maybe the erroring server itself can try to process the order again after it's been recovered, right? So the point here is that, the recovery mechanism may touch a lot of your code. It may even be part of your architecture, right? And then other possible recovery mechanisms are things like this. So if some code fails somewhere, maybe you can try to manually fix or reset the state in the program. Maybe you can try running the operation again, right? So in the case that it happens to be a race condition, maybe it will work if you just run it again. I don't know. And if it's a sub-program where the error is, then maybe you can just restart the sub-program, right? And then maybe it will work. And, maybe in case something goes wrong, you have a backup program hosted on a server, right? So then if the client can't do the correct things, maybe we'll call on the server instead. And, maybe you have a backup program with less features than the main program, kind of like fallback features or fallback code. So again, if the thing isn't working, maybe you run the fallback, which has less features, but the critical part of it is going to work or something like that, right? And of course, even if you do all of that, if a critical part of the program is buggy, then maybe you can't do anything about it, right? Maybe you just literally need to go in and fix the source code. So along with all of that, you'll probably also need to do risk analysis. And that's where you consider things like what code could have errors? How likely is it that errors will appear in that code? What impact would the errors have? Like, are they in a critical piece of the code or in a non-critical piece, right? What would it cost to prevent the error from happening or to implement recovery mechanisms, right? Like risk analysis kind of things. Having said all of that, The basic idea is that error recovery is going to need to be something you really think about when you're doing defensive programming, and it might even need to be part of your feature planning, right? It's a first-class citizen of your project, basically. And also note that, as we sort of mentioned, that this is sort of an extreme case. You need to have quite a critical program to try to recover and, have error recovery mechanisms just in case errors come up, right? So, for most programs, you don't need to go to this extreme. If you just restart the server or something, or if you just notify the user that something went wrong, that tends to be good enough. All right, so we're coming towards the end of defensive programming here, and the next section is on downsides of defensive programming. So if it wasn't clear already, here they are summarized. It can have significant downsides, right? It requires a lot of code, right? Because of all the conditions and checks that you're going to have, the additional ones. And performance can be worse, again, because of all the conditionals and checks and stuff. And it makes the code harder to work with because there is a lot more code, right? And error recovery can take a long time to plan for and implement as well. So with all of that in mind, when should you use defensive programming? It depends on your program, right? As mentioned earlier, some programs need that maximum availability, reliability, and security, okay? So that's when you do it. For everything else, you shouldn't need much, right? As long as you do your normal programming properly, that should handle all the bugs, right? And of course, if you want to use defensive programming techniques here and there, feel free to do so. That's fine as well. But regardless of what you do, remember to be pragmatic, right? Consider the overall health of your project and what your project needs, and do risk analysis, right? Like as we said, what could go wrong? How much chance is there of it going wrong? What would the impact be? And can you prevent it? And what would it cost to prevent it? Things like that. Okay, that was really long, but there really is a lot to cover, right? But that's it for defensive programming for now. Next, we move on to offensive programming. So with offensive programming, the goal is to catch bugs as early as possible and to crash the program immediately. And that's very useful because, well, primarily it's explained in the other video how to respond to errors, right? But just very quickly, it means that you're notified of bugs straight away and that the stack trace is also closer to the cause of the error and is more useful and things like that. So that's the goal. Now, how do you actually do it? So first of all, do normal programming, okay? So everything we spoke about before, about you need your checks, you need to handle certain errors, that still applies even if you're doing offensive programming, okay? Now, don't recover from bugs, right? Like, don't do defensive programming, basically. 3, write code in a way where bugs are obvious and easy to find, and we'll talk about that in a minute in a bit more detail. And 4, immediately crash the program when you encounter a bug, okay? So the weird one here might be the write code in a way where bugs are obvious and easy to find. So let's talk a little bit about that. So essentially, you want to avoid code that can hide bugs. And some code like that are things like default values, default state, things like inheritance, like fallback implementations and things like that, okay? And as an example, for example, why a default argument for functions might be bad, because essentially you might call a function with incorrect arguments, right? You might call a function with an argument that's null, that's not supposed to be null. So by definition, you have a bug, okay? Because when your program does something that you're not intending to do, that's a bug. So you have a bug here, but because the function has default arguments, it's going to work, right? The call is probably going to work. The program is not going to crash, but it might do the wrong thing. So you have a bug that you might not catch, and that is just extremely bad. So that's why you want to avoid things like default state, default values, and fallback implementations like that. Because again, the same thing can happen with like inheritance, right? So you have a parent class and it has a method in here that you're intending to overwrite in your subclass, but you forget to overwrite it. The code still works, but it's buggy, right? It's not doing what you intended to do. So yeah, avoid those kinds of things. Now, the other thing with offensive programming is that you want to catch bugs as early as possible and crash the program. So similar to what you did in defensive programming, you might have additional checks to catch the bugs early. So let's talk a little bit about that. So I know, as I said, you might have additional checks, but not everywhere, okay? So some buggy code, for example, here is some code on the screen. Some code that's buggy is going to crash on its own. You don't need to do anything else to it, right? So for example, if you look at the function foo, if we have a null check in there, it's not going to crash, right? So if array happens to be null and we have a null check, the code is not going to crash. So that is really bad, right? We want the code to crash. So instead, have the second version where we just try to use the array as though it's an array. And in this case, the code is going to crash on its own if there is a problem. So don't add a check, just leave it as it is without a check, all right? And having said that, some code isn't like that. Some code needs to have checks. So for example, some code that might need a check is something like checking that you have the correct state in your program, right? So if you have the wrong state, then the code may not crash. It may just do the wrong thing. So you might validate at some point that the state is correct right now, right? And if it's not, crash the program. And another example is something like the code on the screen there, where the switch statement, right? So in this particular case, the default case is never supposed to run, right? So if it does happen to run, manually crash the program, right? Because that's what you do in offensive programming. Crash the program and fix the bug. And another thing is the get current player health function, all right? So if the code is correct, the player's health should always be between 0 and 100 inclusive, okay? It should never be outside of that range. So in this case, we have a check. We've actually added a check in there to validate that. And if the check fails, then we manually crash the program, right? That's the idea. We want to crash as early as possible. Now let's talk a little bit about assertions. So traditionally, these kind of checks where you crash the program are done with assertions, okay? Not if statements and things like that. And assertions are basically bug finding tool. Like that's their entire purpose. It's if this thing fails, you have a bug, right? But conditional statements, that's not their purpose, right? So if in a conditional statement, the condition evaluates to false, it doesn't mean you have a bug. It just means run other code. You know what I mean? So, that's why you might want to use assertions, because for assertions, it's literally like, okay, you have a bug if this thing failed, okay? Now with assertions though, bear in mind that in some programming languages, they crash the program, right? Like they're doing offensive programming. But in some other programming languages, they don't crash the program, right? They just print an error stack trace to the console or something like that, or they log an error stack trace. So both are usable, obviously, and both are very useful. But if you're going to do hardcore offensive programming, you want to crash the program. And additionally, for performance reasons, and maybe user experience reasons as well, some programming languages allow you to turn off assertions in production. This has some advantages, right? Because if you had conditional statements, you cannot turn them off, and they will crash the program. But if you don't want that to happen in production, with assertions, most programming languages give you the option to basically turn those off completely, right? Now, some downsides of offensive programming, because it has downsides as well, it's a little bit similar to defensive programming, right? So one downside is that it's additional code that you need in your program, right? Additional checks and stuff. Another downside is that you have to avoid certain kinds of code, like, as we said, default arguments. And, default arguments have valid use cases, right? They provide reasonable defaults and they can make the code easier to work with. So, it's not always great that you can't use default arguments, for example. And another downside, of course, is having to crash the program, although that one is debatable because, as we said, for assertions, you can turn them off in production. So essentially, you gain all the benefits during development, and you don't have to crash the program in production, right? But another downside is performance, because again, you have more checks and stuff. But again, you can probably turn it off in production. So yes, so those kinds of things. Now, when should you use offensive programming? Well, basically, offensive programming helps you catch bugs, right? I'm not going to repeat that point again. We've already spoken about it. But that's really good. So at the very least, it's probably really good to use during development, except maybe for the code features like default arguments. Like maybe you want to say, okay, I'm not going to use offensive programming because I want to use those features, that part's fine. But still, all the bugs you can catch during development is a win, right? Like there is no downside to it, especially if you can turn off the assertions in production. Now, for production itself, it depends. Realistically, most programs will never choose to have assertions in production because of performance downsides and crashing the program. But some programs might, right? Like, some programs might naturally decide to crash if an error occurs in production, and that's what they chose anyway, without thinking of offensive programming. So in that case, that's completely fine. All right, so yeah, this was very long, but we're practically done now. Just a final note on being pragmatic, okay? So regardless of what you choose to use, defensive programming or offensive programming, just be pragmatic, okay? Do what is best for your program. So generally, normal programming is something that you must do, okay? If you don't do that, then like you've got bugs in your program. And for defensive programming, you probably want to be wary of using it because of its big downsides. But that's not to say that you can't use a feature or two or a check or two in some critical places. And of course, if you're working on critical software, then you might need to use a lot more defensive programming, okay? And finally, offensive programming helps you catch bugs, which is really good during development. So as much offensive programming as you can use, that's probably a benefit, especially if you don't have to use it in production. And of course, you can mix and match all of the approaches because, again, you need to be pragmatic and do what's best for your code in your code base. All right, that's it. That was a very long video, but there really was a lot to cover. I hope it provided some value to you, and especially like the things we spoke about, I hope they make sense. And even if this video didn't cover absolutely everything, I hope it gave you enough understanding so that you yourself can go out and you have an idea of what you need to do and why in your own code. So if you like this video, please click the like button. Please subscribe if you want to see more videos from this channel. We have many more coming up, including some more on error handling and also many other topics. And as always, if you have any comments, if you have any disagreements or anything you want to discuss, then please leave a comment below. All right, thanks very much and see you next time.